Thank you all for coming back, and we're just going to get started. So we'll have this keynote will last for about 40 minutes. We'll then do a Q&A, and we'll then take a break for about 10 minutes and come back for our panel. Thank you.
Okay, good morning, everybody. It's great to be here. Thanks you all for coming. So I'm going to talk a little bit about how to evaluate technological change. We've heard so many predictions. How do we know what to believe and not to believe? And yesterday, we heard from these two great 20th century philosophers, Barra and Bohr, who both are attributed with a quote, "It's hard to predict, especially the future." And I got to say, coming here, it's hard to sort of fathom all the predictions that you get. I mean, I'm used to much smaller, simpler predictions, right? So I'm used to going to conferences where, say, Chris Manning has a paper that says, my parser got 92% correct compared to DK and Lynn's only got 91% correct. That's the closest we get to kind of talking trash in the parsing business, In your face, Jarniak. But we're arguing about 1% there. And at this conference, we're hearing things about 100% differences or more, right? So here's Steve Kirsch on the left, who's made the prediction that within 90 years, humans will be extinct because of climate change. And on the right, Aubrey de Grey says he's going to live to be 1,000 years old. So at least one of them is 100% wrong. And maybe both, but how are we going to tell? And last year, Doug Hofstadter said that artificial general intelligence is at least 100 years off. And Ben says, no, it's less than 10 years. So maybe that's not quite 100%, but there's a big disagreement there. We've all seen the Kurzweil graphs saying that progress is increasing exponentially, and so on a logarithmic scale it should be linear, and boy, that looks pretty linear. But other people look at the same data in different ways. So here's Jonathan Huebner has this paper called The Possible Declining Trend for Worldwide Innovation, and he looks at pretty much the same data. He's looking at important events in the history of technology. He has one little trick in that he looks at events per year per billion people rather than just total number of events. But by his count, it peaked around 1900. We were inventing relativity and the automobile and stuff like that, and it's all been downhill since then, according to his analysis. And amazingly, by 2100, there'll be zero innovation. So again, one of these guys has got to be at least 100% off. Some predictions I note that are being made are already false. So one of them, and I guess it depends on how you evaluate these predictions, but for example, Wendell Wallach yesterday predicted that within 10 years, computer error would lead to a catastrophe with many deaths, and he said, but maybe it's not quite as bad as 9/11, but it's going to be bad. Actually, if you look at it, today in the US, there are about between 100 and 200 deaths every day from medical error. And many of these medical errors have to do with computers somewhere in the path. So these are errors like giving the wrong drug, computing the wrong dosage of a drug, 100 to 200 deaths per day. I'm not sure exactly how many of those you want to attribute to computer error, but it's some proportion of them. And so it's safe to say that every maybe 2 or 3 months, we have the equivalent of 9/11 in numbers of deaths due to computer error and medical processing. Okay, so that's already happening. It just doesn't seem quite as catastrophic because it's spread out over time rather than occurring in one place at one instant. Arthur C. Clarke got a lot of credit, I think deservedly so, yesterday for his predictions and his stance on predictions in 2001 and so on. But here's a novel from 1986, just 20 years ago, and it's about future, 1,500 years in the future, when scientists discover that the sun's about to go nova, and so they have to save all of humankind's knowledge and send some starships off and repopulate the stars. And so they go about collecting all the knowledge, And so, you know, they're scanning all these books, or maybe they're digitized, it doesn't quite say. And they're actually throwing out novels that they say are not good enough. So, you know, maybe you keep all the Jane Austen, but some of these other authors, you know, will only keep one of their novels, not all of them. And this is supposed to be 1,500 years in the future. Meanwhile, you know, today at Google, and, you know, and I could say that they ended up with a few billion pages when they were done with this sorting process. Today at Google, we have tens of billions of pages. We keep every novel, and we keep tens of billions of pages of spam. You know, we don't care. And according to Clark, you could have one user searching that database, and they would get back an answer in a few seconds. We have tens of thousands of simultaneous users, and you get back an answer in tenths of seconds. So here we are, a prediction about 1,500 years in the future, but after 20 years, we've exceeded the prediction by, well, count them all up, about 1 or 2 orders of magnitude in the number of pages, 1 order of magnitude in the speed, and about 4 orders of magnitude or in the number of simultaneous users. And I guess we can take the next 1,480 years off because we're so far ahead. Okay. It's always fun to look back at what happened 100 years ago and compare that to predictions we're making for 100 years in the future. So Ladies' Home Journal from December 1990. Some things they did really well. So they said that cars and houses will be artificially cooled. Maybe it's, I don't know if it's artificial general cooling or just specific cooling, but they got that one right. They said there would be aerial warships, forts on wheels, which I took to be tanks, I guess, and giant guns that could destroy entire cities. Excuse me, 1900. Yeah. I'll go in and edit that, sorry. Slip of the, this is from 1990, 100 years in the future. They're making these predictions. Photographs will be telegraphed from any distance, so there'll be faxes or maybe internets, and photographs will actually be in color. I got that right. And then there were some bizarre ones. There'll be no C, X, or Q in our everyday alphabet. All right, because they thought that the future couldn't tolerate this kind of redundancy, and we'd use the other letters instead. Why that was one of the most important predictions, I don't know. And then there was a bunch they got wrong. So there'd be no mosquitoes nor flies. No wild animals except in zoos. And they thought this was kind of a good thing, right? That was another bizarre outlook. Rats and mice would be gone. The horse will become practically extinct because we'll have these motorized vehicles. And there'll be fast electric ships going from New York to Liverpool in just 2 days. So this is simultaneously under and over estimating because, of course, you know, it takes us about a quarter of a day to get from New York to Liverpool by plane, but our best container ships take about 4 days. And so they completely missed, they knew that there'd be air machines, but they thought they were only going to be used for blowing up cities. And overall, they got a pretty good mix. So there were 12 predictions where they didn't go as far as we actually have achieved, 7 that they got about right, 8 where they were too conservative, and 3, like the C, X, and Q, that were just totally bizarre. So I tried to look at how we can evaluate what predictions to trust and not trust, and there's not very much literature on it. But one book that I thought was pretty interesting is this by Philip Tetlock. It's called Expert Political Judgment, and he actually looked historically at these people who appear on Sunday morning TV shows and make predictions about politics and analyze when they got it right and when they got it wrong. And the thing he came up with, this hedgehog and fox analogy that I never understood. Maybe I don't know enough about hedgehogs and foxes. But he says that people that were driven by a grand unifying ideology mostly got things wrong, whereas people that were able to look at lots of different data from different data points and compare one to another and say on the one hand this and the other hand that, they had a much better chance of being right. And he says, subject matter expertise translates less into accuracy than it does into overconfidence. So it actually doesn't matter that much how much you really know about the subject area. What really matters is how confident you are about your own ideology. He also said that the more famous you are, the worse you do. And actually, he quoted Google in there and says there's a 0.26 correlation between overconfidence and number of Google hits on your name. So, you know, if you see these talking heads on Fox News or whatever, and a quarter of their incompetence can be explained by their famousness, and I guess the other 3/4 is innate. But I think one of the great morals of this is that your own opinion can be as good as the experts. So you don't need, you know, the PhD and the 20 years of experience in the field in order to get these predictions right. Even having that doesn't help very much. What you need is to be able to kind of read the papers day to day, catch up and so on, and understand what's going on, and being able to evaluate two sides of an argument. And if you can do that, you're as qualified as the experts. So that's good news for all of us, is that you don't have to listen to the people on stage. In fact, there's a 0.26 correlation why you shouldn't listen to the people on stage. And instead, you should evaluate all this stuff yourself when you get home based on all the evidence you accumulate. OK, so that's the moral about judgment. It's kind of depressing. So now we have to actually go back and look at the data. And the Kurzweil type stuff seemed to be inconclusive. Kurzweil looks at it one way, Hübner looks at it another way, and he sees different things. And maybe that's not too surprising, because it relies on these lists of what's important, and that's all very subjective. You know, for all I know, you know, the dinosaurs 65 million years ago, they had a Kurzweil-style chart that says, look, all the really important innovations happened in the last few years. There was this new kind of plant that evolved that's really delicious, and you know, that was really the most important thing that's happened for millions of years, and all these new things are happening really quickly. So from any one point of view in time, it may look like the important things are happening now, but you really want to see if they have an impact on the world in a more objective sense. So one of the things you can look at is gross domestic product. This is the total GDP for the US, inflation adjusted. Where I got this slide from, they were trying to point out these sort of depression and recession points. The Great Depression in the 30s, you can actually see a real drop there. This littler recession due to the oil crisis in the 80s, you can see a little blip there, but in a couple of years it's gone. And you know, if you draw a straight line, it's all pretty straight there. So a definite dip in the Depression, a little blip in World War II, where production was sort of artificially pumped up by borrowing from the future. But again, a couple years after the end of World War II, that blip is all gone. So what this says is that there is constant progress, exponential progress, because this is a log graph, so linear on a log graph is exponential. But it also says it doesn't seem like there's any great acceleration due to technology. So there's no takeoff in the 60s after space technologies, or in the 80s after personal computers come in. It all just pretty much seems pretty flat. Another way you can look at it is by looking at percentage annual growth. And here, you know, I swapped around and I looked at the world rather than the US, and I'm looking at per capita rather than total. But it looks fairly constant. And so, you know, as you go across, it looks like, you know, most of the annual growth is between 1% and 2%. Certainly, almost all of it is between 0% and 3% a year. It doesn't seem like it's going, there's any solid trend up or down. In fact, over this period, from 1970 to the present, the annual growth rate was 1.6%. And world GDP is about $6,000 today. So if this 1.6% continued in the year 2100, that would give us 26,000 median GDP. If it bumped up to 3%, that would give us 92,000 median GDP for the whole world. So either way, that's a pretty good advanced that we're looking at if things hold along this course. It means you know, most of the people in the world would be brought out of poverty up to a level that looks pretty good today. But again, we don't see any real accelerating trend. We just see this constant 1.5% plus or minus a percent per year. Another objective stat you might want to look at is life expectancy. Here, this is a linear model, not a log model. So now the progress is not as accelerated, not exponential. It's just linear progress going up on, this is from 1950 up to 2005, going up on every continent except in Africa, which starting in the late 80s had this hit mostly due to AIDS and is falling behind the rest of them. The other continents you see going up and you see squishing closer together. So South America and the other continents are catching up to North America in life expectancy. But again, no market acceleration due to increased use of computers or any other kind of technology. It all looks pretty flat. It seems like no matter what you do, it's not going to make a difference. Okay. So now I want to talk a little bit about artificial general intelligence, but in order to do that, I want to make some analogies. So first I want to talk about AGS, which is artificial general space exploration, a term I just coined. So this is the analog mission at the Houghton crater in the Arctic in Canada. And what we've done there, and so this is a mission that I was involved with in my former life at NASA Ames, where we sent up teams to simulate what it would be like being an astronaut on Mars. And the conditions in this crater in the Arctic are, in several ways, are a good analog to being on Mars. And we wanted to understand what it was like for a team of astronauts to be there and try to live and do explorations and go out and do science every day. And so this was really AGS. We were trying to say, let's attack the whole problem of space exploration, or in particular Mars exploration, and see if we can get it done, understand the problems, and see how far that can go. And that was an interesting project. And I think it was an important one. It was worth doing, and that's why I supported it, and it's ongoing. But it really seems to me that if we get to Mars, that's not going to be the bottleneck. You know, it's going to, things that come out of that are going to be very important in terms of getting the maximum return per hour for an astronaut on the surface and for having them all get along and not kill each other. But the step that's going to make the difference between going to Mars or not is not going to be this AGS, this generalized space exploration. It's going to be all the components. And here's one example. This is my pal and former colleague, Les Johnson from Marshall Space Flight Center. He's holding carbon fiber material that could be used to build space sails. And probably space sails are not the particular technology that's going to be the key breakthrough for going to Mars. But there's going to be a lot of them. And they're going to have to do with propulsion and radiation shielding and control and launch and transport into low Earth orbit for cargo economically, and so on and so on. It's going to be these components that are going to enable us to do it. And it's not that we don't know how to put it all together. It's that we don't have the components. Okay. Now, here's another field I just made up. Artificial generalized materials science. Okay, so materials science is a fascinating field this way. You've got these carbon nanotubes over on the left. I don't know if you can read this, but this is the first biological film. So they've grown this photographic film, a team of students at University of Texas. At the bottom, we have this incredibly strong structure built out of diatoms from the Kiesling lab at Berkeley. And so all this great progress in materials, but nobody in that field is saying, gee, what we really need is one thing that makes all these possible materials. That's not where the field's going. Instead, they're saying, there's these exciting breakthroughs. Let's all work on them all individually and then see where we end up. And by the way, one of the things I think is, you know, I think this whole field of synthetic biology is absolutely fascinating. I had a chance a while ago to talk with Craig Mello, who won the Nobel Prize for RNA interference. and talking with him and picking his brain about how exciting all this stuff was, and how I was interested in it and saw this amazing future for these kinds of materials, this kind of biology, synthetic biology and so on. And then he told me that what he was really excited about was the future of AI. And so I thought that was a little ironic, but I also took it as kind of a bad sign that each of us who was an expert in one area was saying, no, this other area, that's the one that's really exciting. But we'll see how it all plays out. Now, another thing I want to talk about is AGC, which is artificial general culture. And I think that's something that's really important. Because if you look at these two guys, there's really not that much difference between them, I think. And sure, if you took them into the lab, you could say, well, this chimpanzee on the left, he seems to be stronger. And this Homo sapiens on the right, he seems to be a little bit smarter. And if we had the third kind of chimp, the bonobo up there, we could say, they seem to be having more sex. So there's these individual differences, but mostly I think they're more similar than they are different in terms of their overall abilities. If you just sort of plunk one down in the middle of the savanna and look at what they're able to do as an individual. So it's only when you compare the cultures that you see this fantastic difference. And there you can really say, the chimps are limited, they have these great family structures, but it doesn't really go beyond that. Whereas look what the humans have been able to do as a culture. And I think that's the exciting promise of what humans are. And it's not their individual intelligence, it's their collective cultural intelligence. And so if anything, we should be looking at that and trying to build this culture rather than trying to build an individual. Okay, so we're back to AGI. And one of the things I wanted to do is say, is there anything different about this point in time right now compared to points of time in the past? And I tried to think about how to evaluate that. And I was inspired by Marty Hurst, who did some work at looking at particular keywords to do extraction from natural language text. And I thought a good keyword to look for is the phrase, unlike previous. So I did a Google Scholar search for artificial intelligence and for unlike previous, and then limited it to different age ranges so I could say, what are people saying about what's different right now at their point in time compared to previous systems in the past? And so this is what I came out with. So in 1968, somebody said, well, I have the system that, unlike previous system, learns from examples. Notice in 1998, we had the exact same thing. And then we're also saying, well, no, in 1988, say, the difference is being able to represent different states simultaneously, and so on and so on. So I looked at a couple hundred of these, and I said, I can't tell the difference. It seems like at all these points in time, people are saying, well, unlike previous systems, I'm building a new one, and it's got something slightly different. But there's no feeling that right now there's anything that's more privileged about us being on the verge of discovering something as compared to comparing 2007 to 97 or 87 or even 77. So what do we need to make progress? Well, I think it's really two things. We need more data, and we need more models of what that data does. And both of them are important. And I think it was interesting that in SIGGRAPH this year, there were two papers that came out that got a lot of press, Slashdotted and so on, and they took two extremes on this poll. So one of them here is this work by Abadan and Shamir on image resizing. And they show how you can take an image and squish away some of the pixels or add in some pixels and get back another image that looks really good. And they're able to do this without any model at all of the world or what the pictures are actually about. All they're doing is saying, take the pixels that are most like the pixels next to them, and they're not adding much information, so just throw those away. And then there's a little bit of clever dynamic programming to say how you slice out a whole path for the picture to do that. So no knowledge about the world at all, but you can see here, you still get pretty good results. You can squish that picture in, or you can extend it out, and it looks great. It's filling in the right stuff without knowing anything at all. Now compare this to another paper that's pretty exciting by Hayes and Efros, and they say, so say you took the picture on the upper left, and half that picture is good, but it's got those rooftops in there, and you don't really like them. So you go into Photoshop and you etch out this mask that you see on the upper right, and now you say, I want to fill that in with something. And if you're an experienced Photoshop user, you could actually clone out some of the water and put it in there, but it would take you a while to do that. So what they said is, instead, let's just go against this database of photos and find some that look similar and fill it in with stuff from that. And so in the lower left, you got this big collection of photos, and in the lower right, it shows one, and then put it in, and it looks just right. It comes out great. And the interesting thing about this is that there was a threshold. So they started off with a database of thousands of images, and it didn't do anything good. It just put in kind of junk there. But once they got past millions of images, then all of a sudden, it started to find matches. If you have a few million images, you're going to find just the right one. You match it in there, and it works great. So here there was this threshold of knowledge or of data that once you pass it, you get the right answer. At Google, we had a similar experience with our machine translation work. So we're able to go from Chinese to English and do pretty well. There's a few disfluencies there, but basically you're getting the right idea. And we're doing this with, in this case, there's both a model and data, but the model is a fairly simple one. So we don't have deep understanding of the world. All we have is a model of what words follow each other in English and in Chinese, and what words map to each other in pairs of text. We take a news story in English, a news story in Chinese, and say, this story is a translation of this story, and then build a probabilistic model that says, well, probably the first sentence is a translation of the first sentence, but it might be 1 to 2 or 2 to 1. Spread the probability over all of that. And then within the sentence, you do the same kind of thing going into the words. This word might translate to this word or might translate to that word. And if you only have a few million words of examples, you get nowhere. But once you start getting up into the billions, you start doing pretty well. And so here you see linear performance, not yet asymptoting out, up to 18 billion words of paired data between Arabic and English. And in the background, there's also an English model of 1 trillion words. So that seems to help a lot. So we're changing the way we look at where the trade-offs are between data and models, and saying if you can solve a lot of the problems with the data, go ahead and do that. Only introduce the models when you really need it. And this changes the whole way that we think about how we do what you think of as everyday programming as well. So you look at, testing is a big thing now, doing unit tests and so on. So you look at what's the API for JUnit. You can assert things are true or false or equals the same or not, or whatever. When we go to test Google, this stuff doesn't really help just by itself. It's not enough because sure, you can break it down into we want this part to be this part of our code, we want this assertion to be true, but really the important things, as we're saying, are not logical truths, they're probabilistic ones. They're saying we want over 90% of the time to get a good answer. And we want that to be against the current state of the web, which changes every day. So it's probabilistic and it's online. It changes this whole idea of how you do testing. It used to be you build the code once and then you freeze it and then you test really hard and make sure it's correct. We can't do that. We have to say, we're in a continuous process of updating. So we're testing this code that's essentially alive and continuously morphing, and we're testing it probabilistically and still trying to get some assurance that it does the right thing. Okay, so that changes the way we work. Let's get back to AGI. And I said I thought that the components were more important than trying to solve the whole problem at once. And once you have the components, then you can solve the whole problem. What do I think are the main components? Well, I'm an expert, so don't trust me. But these are the things that I think we need progress on, and there is progress currently being made, so I am encouraged, but we still got a ways to go. So I'd like to have probabilistic first-order logic. So I said that a lot of when you interact with the real world as opposed to an artificial world, you're dealing with uncertainty, so you have to deal with probability. Traditionally, most of the probabilistic models have been propositional rather than first order. Means you can talk about the probability of it's raining, but you can't express complex things like for all positions, if it's raining now, then tomorrow it won't be raining, or this sort of ability to quantify over multiple states rather than talk about individual states. So that's going from propositional to first order. And it's been difficult to combine those, but groups at Stanford and Berkeley and other places are making good progress on it. We need hierarchical representation and problem solving. So we have a lot of ability to do planning and problem solving. We have ability to come up with different representations, but the real question is making this hierarchical, to be able to, to solve the vision problem, to go from pixels to lines to faces to people in a crowd, and build up each of those in a hierarchical fashion. That's proved difficult to do. Then you need to be able to do learning over all of these. You want to be able to learn from the data rather than having to program it by hand, or we're never going to get anywhere. You want to be able to do that with lots of data on an online fashion, continuously updating, and do it efficiently. And if you can do all that, then once we have those components, then I think the time is right to start thinking about AGI. Okay, and I think we have time, 10 minutes or so for questions.
Go ahead.
I wanted to ask you a question about innovation. I think there was a chart you showed there after Ray Kurzweil's that was particularly showing a decline in some sort of measure of events over the 20th century. And I think that's been consistent with a number of observations made by some writers over the last 10 years. I think Charles Murray had a book called Human Accomplishment, and there's a book recently about physics by Niels Bohr called The Trouble in Physics. And I think a number of people that I've talked to as well have felt that over the 20th century, although we're scaling up science projects or increasing the diversity of PhD programs, interdisciplinary programs, that we're basically training very highly skilled technicians who are extremely knowledgeable in a domain-specific area. And of course, you've referenced later on about the trade-off between breadth and depth in expert prediction. I was wondering if you had any comments about that with your experience in academia or industry.
Okay, so it's hard to repeat the whole question, but it's about, I guess, big innovation versus small technological tweaking, and saying, maybe all the good ideas were done in the last century, right? So, Einstein got the relativity. There's not that much left in physics. So all we're doing is building these little devices and making them a little bit better. I think, for the most part, I don't think I believe that. I think that it takes time to see something as a big innovation. So maybe that's why the people who make these predictions say so. Again, I don't trust these lists of this was important or this was not important. So I think there's still a lot to be done. I think that as an individual, you have much more power now to do something, to go out there in the world and change the world. Whether there are fundamental things that are going to advance as much as they did, in 1900, I don't know. I think there's still a lot left to do.
You have, I think what I was trying to get at was not so much what is the open problem, but rather the training system, the sort of.
I see. So the training system, is it that we're pushing the students in the wrong direction, and that's why we aren't getting innovation, because we aren't letting people focus on the basic stuff.
Okay, excellent.
I guess I don't believe that, because I think that the people who are going to make those kinds of breakthroughs, I don't think you can stop them, and I don't think you need to train them. So, I think if Einstein's going to do it, he's going to do it because he's Einstein, not because he got the right training. And
Okay, so we'll go to the guy at the mic, and then we'll go to Rod.
Excuse me. Do you think that when we actually get to an AGI, we're going to notice it, or is it going to be part of a transition where our tools seem to be getting better and better, and we look back, and it'll be kind of like the Turing test of folks sort of arguing as to whether we passed the Turing test a while back? Is it just going to be a smooth transition?
Yeah, I don't think there'll be a single point where we said, you know, at such and such a date, you pulled the switch and this thing took over the world or whatever. Somebody said yesterday that the singularity is a period, not a point, and I think that's right. I think you'll see increasing capability, and you'll get more and more used to it, and you'll say, wow, you know, this is a little bit better than it was before, and it's only in retrospect that you go back and say, you know, things now are much different than they were a few years ago. But you know, if you believe these exponential curves, you know, the derivative's always the same. So you never notice this acceleration and change.
Peter,
Right.
one of the common themes in Hollywood has been you get the big network of stuff, and out of that comes big surprise. So the Forbin project, Terminator. You guys have built the biggest thing. I'm pretty sure that you haven't got, you know, AGI isn't working within there. But have you noticed any emergent property of the bigness of your network of stuff with all these agents working together that has been a surprise?
Okay, so is there any emergent property of Google that's been a surprise? So certainly we notice things about the bandwidth between computers that we never expected, right? At a sort of a very low level. You know, we programmed the system and we tried to build these abstractions that said you can define a job as various components, and we'll have this architecture that spreads off the sub-jobs among multiple machines, and it tries to allocate them in the right way. And most of the time that works right, and some of the times it just doesn't work at all. That for some reason there's interference and crosstalk and so on between these, and we just aren't getting the bandwidth out of these switches that we think we should be getting. And then you look at it carefully and you say, you know, now I understand. I put this job here and this other job over here when they actually, they had to have been together. And so we get those kinds of surprises, but I don't know if that's exciting enough for you. I guess the other thing that I hadn't really thought about when we started this all is how kind of game theoretic the whole thing is. And that at first we thought of ourselves as this observer of the web, that the web was out there and we made a copy of it and indexed it, and if people wanted they could come and access that index, but it was just a reflection of the web out there. And now we understand that we're co-evolving with the web, and that when we make a move, it changes the web. When the web changes, we change, and it's going back and forth. And so, you know, all the search engine optimizers and so on are watching what we do, and we watch what they do, and the web, the interaction between us. And that's something that I hadn't even considered before we saw it happening.
We're with NASA, and I guess you have an interest in space exploration. But my argument in recent years is, why would we send humans to Mars, considering the time frame? And really what we're looking at is the opportunity cost of spending that money to throw 200 pounds of protoplasm on Mars to hit a golf ball versus the research on what we're doing right here, what we're talking about right here, which is really fundamentally important, I think, compared to that. I mean, I know that involved in that program, you want to do this, but should we do that?
Right. That's why I wanted to go to NASA, is because I wanted to send robots that were capable rather than sending humans, because it is so much cheaper. One, the robots are happy with a one-way ticket. And then the astronauts, although, actually I was in a room once with a bunch of astronauts, and every single one who did not have a family was willing to take the one-way ticket to Mars. But for political reasons, the powers that be would not be willing to sign on to create such a mission. So it's you know, exponentially more expensive to have a round trip ticket because you have to not only get there, but you have to send enough fuel or build enough fuel when you're there to get back. So my take was, robots are the way to go for the foreseeable future. Let's try to change the agency to go in that direction. And to a small degree they have. The robots that are operating on Mars now are more capable than the ones we have in the past. They're tremendous success, far outlived their life expectancy, and they're doing a good job. But I was not able to change sort of the overall sense of the agency, of saying, these rovers are nice, but they're really just precursors for sending the humans, because that's the important thing. And I think that's partly, the way they operate. It's partly they think it's a human relations type issue of saying, the public will only fund us and send a lot of money if they get to do the exploration of sending people. I think that's probably not true. I think the public's pretty excited about robots, and as long as they can see the videos on YouTube, they don't really care if it's a human or a robot holding the video camera. But I wasn't able to make that change, and so I did something else instead. Who do you want to call on? There.
Yep. Trying to get something we haven't had before. So yeah, in the green. Yeah.
Yeah, so a bunch of people working on it. Daphne Kohler at Stanford, Stuart Russell and his group at Berkeley, the Cognitive Robotics group at Toronto, and there are others. And so, part of it is defining just what it is that you want to be able to say. And so, there's always a trade-off between expressivity and efficiency of your logic. And so trying to choose the right subset where you can say the important things but still get the ability to do the processing. And then the second part, and as you get more expressive, it becomes more difficult, is actually being able to do the inference and do it efficiently. And if you're doing approximations, have the approximations be close enough. And so these things are coming along. You can do things now like one of the examples was trying to do citations, figure out authors of books when, as you've noticed, if you've looked, most of these citations are wrong, right? So, they'll spell the author's name wrong, they'll leave out the middle name, they'll put the middle name in, they'll get the title or the journal slightly wrong, and then you have to figure out, are these two citations to the same thing or different things? And so you need a first-order logic because you have to quantify over all possible papers, authors, and institutions that the authors come from, and then you need to reason about identity between them. And that type of problem can now be solved, whereas a few years ago we couldn't have done that.
Okay, we've got time for one more. The guy at the mic.
Hi. For the last question, I'd like to go back to the first question about the possibilities of technicians being trained rather than scientists, because it seems to me that the suggestion that Einstein would have done what he did in any context seems perhaps to be ignoring the fact that he was the son of an electrical engineer and went to get a PhD in physics and was given this special opportunity to, based on standardized testing in this case, and despite failing in school. And basically, it seems to be ignoring what you said earlier about culture being much more important than the individual differences in intelligence. You pointed to the chimps and the skyline.
Right.
So do you have any comments reconciling those two positions?
Yeah, so I think, certainly Einstein's family and schooling and, both formal and informal, and he was in communication with other physicists and writing letters back and forth and so on. So that was all necessary and important. I'm not saying that he did it alone. He did it because he was in the right place at the right time, and somebody had to do it. And if he didn't do it, somebody else would have done it 5 years later or 2 years later or whatever. So it is the culture that eventually comes up with a solution, not so much one individual. But I guess what I was trying to say was that he had this drive to do this, and he wasn't in the best of situations, right? He didn't get a good academic position to start with. He was stuck in this patent office. He was doing physics in his spare time, but that was enough.
But maybe
for him.
that suggests that working in the university is a worse position to do your research from than working in a patent office. Maybe that's a terrible indictment of the university system.
Yeah, I think you want more data points to do that. But I mean, I think if you have the inclination, you'll seek out and do the best you can within the culture that's available. And I think that was true back then, and I still think it's true today. That even if there are pressures to go in one direction or another, if you want it enough, there's enough freedom today that you can do what you want to do.
Great. Thank you, Peter.
All right.
Thanks for that. It's fantastic.